Now we will discuss about another most important block cipher, that is called AES. So before going into the details, let's discuss about the history besides this AES. So in some point, people think, okay, we need a replacement. Not people, that national agencies, they are looking for something new rather than DES, because and at some point DES seems like it's lost its usefulness. Okay, because there are some lot attacks like special purpose crackers and distributed attacks on the internet. Through this DES is broken. Then they created a 3 DES. I mean, we do DES 3 times, but it is not very efficient in software code, and it is too slow because we are doing it 3 times, and it is a 64-bit block size. Okay, so it's a 3DS is not a solution for long-term use. Okay, so in 1997, NIST made a formal call for advanced encryption standard algorithm. So it is open for all. Okay, many people from all over the country, they submitted their algorithm. It's like that. Uh, so the goal was that competition is to replace DAs for both government and private sector encryption. So there are some requirements, like it should be unclassified, and the encryption algorithm should be disclosed, and it must implement a symmetric key. And one of the major requirement was the block size should be higher than DES. So DES is 64, but here in AES, the block size is 128, and the key size is 128, 192, and 256. There are three kind of key size in AES. So in 1998, that NIST announced, that is not very old. Okay, so in 1998, NIST announced that they have received 5 candidate algorithm. Okay, and they actually look for security, robustness, and speed of this algorithm. So IBM, they proposed Mars, the RSA laboratory put RC6 algorithm. Okay, Regendale algorithm developed by two people, Damon and Ridgeman, I think, and some other, two fish, serpent, etc. So among these 5 algorithm, the Rindsdale algorithm became the AES. So they actually have the winner. So it is pronounced at Reyndal. Okay, and it is so Reyndal algorithm became the AES algorithm in 2010. So only 20 years ago. So the main feature is it is designed to be efficient in both hardware and software. So there is no, yeah, in DES it was the Feastel network, but here there is no Feastel network. Uh, it is said by Shamir is secure forever. Okay. So if I give you the overview of AES, now you have to be very, you have to put your attention from now. Okay. So the block size is 128-bit. The key length is different, 128, 192, and 256. And here we have round 10 to 14 rounds depend on the key length, and each round there have some functions like byte substitution, shift row, mix column, and round key. Okay, it will be more convenient to see the graphical representation. So this is our simple AES algorithm. Okay, so we have plain text of 128-bit. We have a key, so it can be 128, 192, 256. But for this discussion, we are just taking the key size is 128-bit. and we get an output of 128 bit. So if we put 128 bit plain text and we have the key of 128 bit, then we will get a 128 bit ciphertext. It's simple. And I talk about the number of rounds. So if we select 128 bit key, the number of round is 10. If we select 192, then 12. Then if we select 256, then 14. So this is the basic overview of AES. As I said earlier, we have plain text. Okay, there is a key addition layer. I mean, that is a XOR between the plain text and some part of key. Okay, just forget about this part right now. Okay. So as I mentioned, we have byte substitution layer, shift row layer, mix column layer, and key addition layer. So this is for round 1. Similarly, we have the same thing for round 2, round 3, round 4, and etc. Okay, so if we see the full picture, it will be look like this. So this is round 1, and the output of key addition layer is go to the next round. We do the same thing again. The output goes to next layer. We do that again into n times. So n is the number of round. Okay. So now I would discuss what actually happen inside this. Okay. So to do so, I will show you a more detailed diagram. Okay. But before that, okay, we have the detailed diagram. But before that, this is the 128 bit. I mean, this is the our text, plain text. A0, A1, A2. We have 16 byte here actually. We have to remember this thing. So we have 128 bit. So we divide it in 16 byte matrix. Sorry, 4 by 4 matrix, and uh, each sorry. So this A0, A1, A2, it contain 16 byte of input. So 16 byte, 16 bytes, sorry, 16 bit, 16 bit, 16 bit. So we will have 128 bit. Okay. And for simplicity, we are assuming this A0, A1, A2, A3, this have hexa number. So suppose A0 have 0, 0, 0, 0, and 0 1 1 1. So this is 8 bit. So A0 is this one, it is 8 bit, but for simplicity we can convert it in hexadecimal. So hexa, this is 0, okay, and this is I think 8, so 0 8. Okay. So this is the internal structure of AES. This is very simple, not too difficult. I will show you. So at first I will just describe what is happening here. This is that our A, as you seen in the last slide. So we have 16A. Each of these A are 8 bit, right? So 8 into 16 is 128. So our A is this one. So what we do, we divide this A0, A1, A3, A3 and put in a S box. We see in DS it work as an input in a S box and give a output. That's it. We will see what is going on inside this S box, but before that, this actually take input this A0 and output B0. For the same case, A1 become B1, A2 become B2. Okay, so I'm just describing the first round. Okay, so it will be same for other round. And the next part is shift row. Shift row is nothing but recombination. So suppose B0 is putting in the first position, B5 then came here, but actually B2, B1 should be here, but we put B5 here. Then B1 goes to some another place. So we are rearranging the position of different rows. Okay, and after that the mixed column. So we'll have something here. So in mixed column we actually multiply something with these B values of B. We multiply it and we get this C value of C, C0 to C15. And finally we take the XOR of this 1 2 3 4. Finally we get this 4C and we XOR it with the key and we get the some values here. So see this value again converted to A0, A1, A2, A5, and this procedure actually there is a loop. Okay, it will iterate to the number of round. So now I will show you in details of what actually happened in here. So this is the byte substitution part. Okay, so in this part, as I told you, there is a S box here. So this is the S box. Okay. This is the X box. So how we use this? Suppose what I told you earlier, A0, we have C2. This is a hexadecimal number. Okay, C2. So we have C2 in A0. Similarly, we have, suppose we have like 2E, 2E in A1. So now I have to look at this S box. So how we'll do that? So in A0 we have C2. So we look for C here. Where is C? C is here. Then 2. 2 is here. So this one. That means C2 is now replaced by 25. I will show another example for A1. A1 is 2E. So 2 is here and go to the E. A, B, C, D, E. 31. So 2E will be replaced by 31. That's it. So for each of this A, we are using this S box. We replace the existing number with some new number. Okay, just remember that these numbers are all in hexadecimal. And also one thing you have to remember, this is, we are in round 1, so this S box is for round 1. For round 2 there is another S box like this. So if we have 10 round, then we have 10 S box. Okay, now we after like these are the output of its S box. Okay, this one, this one, this one. So now we have this B, values of B here. So now what we'll do, we'll do some shifting. So B0, maybe B1 moves to some another place, B2, B10 moves to another place, B6 moves to another place. So there are some rules how to move. Okay, So and after this shift row there is a mix column, and I said we multiply these values with something, some matrix actually, and we get the value of C. So let's see. So here is our that B value. Okay, B0, B1, B2, B3, B4 till B5. So how we get B? We initially have A, then we put it in a S box. Okay, and we get B. Now what we'll do? Now we will rearrange the B. So how will we rearrange B? Here is the B. So this is a, if we put it in a 4 by 4 matrix, so it will look like this 4 by 4 matrix. So the output matrix is, for the first row is the same as this one. I mean there is no shift. What we are going will do here, we'll do some shifting. So B0, B4, B8, B12, there is no change. For the second row, I mean if this is row number 0, if you do the indexing 0, 1, 2, 3, so number 1, so we will make one position left shift. So left shift means B5 will move to B1, B9 will move to B5, B13 will move to B9, and this B1, this will move to B13. So B5 came here, B9 came previous position, B13, B1. Okay. So number index 2, we make two position left shift. So two position means 10 I will shift it to, so it will come here. So B10 move to position of B10, B2. Okay. B14 also move in B6 place, 14. So it is like a round robin scenario. So B2 will move to B10 and B6 move to it. Similarly, for the third row, we have three position left. So in the shift row sub layer, what we will doing, we have this input matrix and we just make a rearrangement based on the shifting. Okay, so the B now looks like this. Okay. So now come to the mix column sub layer. So this is our output matrix. We found it from the previous layer. So what we will do, we take the first column. We take the first column here and multiply by this fixed size matrix. Okay. So this four column, we have a four column here, 1, 2, 3, 4. So this four column is multiplied by some fixed matrix and we get C0 to C3. So for if we compute the whole matrix, so we will get C0 to C16, C15. Okay. So now we have C0 dot C15. We are just adding something here. Okay. So mixed column part is finished. So we'll have now the C value. So we are just, what we are doing here, we combine all this C and doing XOR with K. Okay. And this value will be go to the next round. In the similar way, it will go round and round. So there is another question here is, now let's talk about this part. So we have done this part. Okay. And I didn't mention earlier, like AES algorithm, there are two things here. One is called diffusion and another one is confusion. I think this one is confusion. There are some properties, okay. Confusion is okay, confusion, because we are actually rearranging everything to create diffusion and confusion. So now come to this part. So we are having k0, k1, okay, k2, k3 till kn. So how to find this k? So k here we have used 128 bit k, okay. So in the how you remember how we convert it into a. So this is same as k. This is for k0 to k50. So 128 bit k is divided into uh, k 16 byte, okay. So and then we make a group here, okay. So we have total 8888 32 bit. So we are saying 32 bit means one word, okay. So this 32 bit key became word number 0. This 32 bit became word 1, word 2, word 3, okay. Then is a simple is here. So this is used for round 1. This value is used for round 2. Similarly, this for round 9, and this part is for round 10. So as I mentioned earlier, there are several round. Like if we take 128 bit, it means we have 10 round. So each round, this key will be used. So this is actually 128 bit, right? So we need 128 bit. So what we are doing here, we take uh, one word, we divide this key into words. So we have got 4 words here. So each word means 32 bit. So in the first round key, we actually send the same key, okay. But in round 1, the key is changed. So how the key is changed? It is just some XOR operation. So in round 0, W0, W1, W2, W3 is used. In round 3, sorry, round 1, W4, W5, W6, W8 is used. But the value is changed. How the value is changed? Let's think about this one. What about W5? So W5 means the XOR of W. Okay, no, not this one. Let's describe this one. W6. W6 is the XOR of W2 and this one. And what is this one? This is the XOR of W1 and this one. What is this? This one is the XOR of W0, and something is happening in this G function, okay. So W4 actually, what W4 is, W4 equal to, we have W0, okay, W0 XOR some function here G of W3. Okay, you get the point. So there is XOR, one is W0 is coming and some output from this G, and the input of G is W3. Similarly, if we go for W5, so W5, I'm writing is like this, W5, it means it is the XOR of this part. So what is this? This is actually W4. This is W4 XOR W1. Similarly, if we go W7 will be W3 XOR this one. What is this? W6. So after doing this operation, we have the keys for round 1. When we do the same operation here, we get the value of this one. Doing the same operation here, we get the value of this one. So these bits are being used in every round. So these are called the round key. Okay. So we are using XOR, right? So this is for a reason. Okay. So how to decrypt it? Because in DES we saw is the same algorithm. We just do it from the end to beginning. So in DES, if encryption is like this, then the decryption is like this. So we have to start from the end. But in decryption, this AES is different. What we have to do, we need to inverse everything. So I'll just show you. So what we will do inverse shift row, inverse byte substitution. Okay. So inverse mix column. So we'll do everything inversely. Okay. So in that case, we'll get the plain text. If you decrypt it, so we can do it by inversing. Because it is not using Feastel network, so we cannot do the same. So we need to be inverted. So as I said earlier, mix column will become inverse mix column, inverse shift row, invert bar substitution. Okay. Okay. There are some other block cipher also, Blowfish, RC6, etc., etc. If you are interested, you can take a look on this thing.